Where is the center of the universe? Is it reliable to say that the universe is 13.8 billion years old? Why can a single element challenge the Big Bang model? What lies beyond the observable universe? And does the mysterious phenomenon known as dark flow actually exist? These are deep and far-reaching questions. Today's content might be a bit lengthy, but I hope it offers you a mentally and emotionally enriching journey. As short-lived beings with limited understanding, our attempt to explore the cosmos might seem absurd. Compared to the universe's immense age, our lives pass by in the blink of an eye. Moreover, concepts we often take as fixed, like time and space, may actually defy our fundamental understanding. That's why when viewing today's content, I invite you to keep an open mind. To begin, let us ask, where is the center of the universe? More precisely, where did the Big Bang occur? To answer this, we must first understand its basic process. Around 13.7 billion years ago, the universe emerged from an extremely hot and dense initial state, a kind of primal soup made up solely of fundamental particles, so energetic that atoms could not yet exist. From that moment, the universe began a rapid process of expansion and cooling, gradually allowing atoms and eventually stars and galaxies to form. This continuous expansion, along with the constancy of the speed of light, has effectively turned the universe into a time machine. When we observe distant celestial bodies, we are actually looking into the past, seeing them as they were billions of years ago. Nearby galaxies appear mature, while those billions of light years away look younger and less formed, simply because their light has taken so long to reach us. It is important to remember, however, that these distant galaxies are just as old as our own. Due to the expansion of the universe, they are no longer in the positions where we currently see them. This kind of universal expansion implies that the universe has no single central point, or, put differently, that every point can be considered the center. No matter where you are in the universe, everything else seems to be receding from you, and all other galaxies appear to be moving away. Of course, the universe does not expand in a perfectly uniform manner. On smaller scales, gravity counteracts this expansion, pulling matter together into galactic clusters, which themselves are organized into even larger structures, a vast cosmic web composed of thread-like filaments of galaxies and immense voids between them. Over time, these voids grow larger due to ongoing expansion. The rate at which the universe expands is described by the Hubble constant, which is currently estimated to be about 80,000 kilometers per hour per million light-years of distance. This means that some extremely distant celestial bodies are receding from us faster than the speed of light. As a result, there is a natural limit beyond which we cannot receive any information, the boundary of the observable universe. Any light emitted from beyond this boundary will never reach us, making it impossible for us to determine whether the universe as a whole is finite or infinite. Even if it is finite, it likely does not have a traditional edge. Instead, it may resemble the surface of a sphere, finite, yet without boundaries. After all, the universe encompasses everything that exists. If it had an edge, what could lie beyond it? So we return to the original question, where did the Big Bang happen? Where should astronomers aim their telescopes to find the starting point of the universe? The answer is, everywhere. From the very beginning, the universe included the entirety of itself. The Big Bang was not an explosion that occurred at a specific spot in space. Rather, it was the expansion of space itself. The Big Bang had no particular location, because it was the coordinate system itself that exploded and expanded. What changed was not where the universe was, but how big it was. About 380,000 years after the Big Bang, the universe had cooled enough to become transparent to light. The image we have from that era comes not in visible light, but in microwaves, what we now call the cosmic microwave background, or CMB. If you had a telescope capable of detecting microwaves, you would see this background in every direction. At that time, the temperature of the universe was still extremely high, around 2,500 degrees Celsius, which would normally emit visible light. However, due to the expansion of the universe, those electromagnetic waves were stretched to roughly 1,000 times their original wavelength. As a result, the ancient photons that finally reach us today are no longer in the visible spectrum. They have become lower energy microwaves. Observing the CMB is like seeing the universe before stars and galaxies ever formed. It is the oldest image of the cosmos that we can perceive. The subtle temperature fluctuations in the CMB became the seeds of all large-scale structures in the universe: galaxy clusters, filaments, and cosmic voids. Fortunately, the universe contains few other bright microwave sources to interfere with our view, making the CMB a relatively clear and undisturbed snapshot of the early universe. But can we see even further back in time than this? At present, the answer is no. Before this stage, atoms had only just begun to form. In the earlier, denser universe, filled with that hot, fundamental particle soup, photons could not travel freely. The universe was opaque to light. And so, the cosmic microwave background marks the earliest visible light of the universe, a silent, ancient testimony to our cosmic origins. So in conclusion, the center of the universe is both everywhere and nowhere. When you use a microwave telescope to observe any corner of the sky, you are in fact looking back in time to just moments after the Big Bang. Now for the second question. How old is the universe really? Is the widely accepted age of 13.8 billion years credible? Modern science generally agrees that the universe is approximately 13.8 billion years old. Surprisingly, the process by which this age was determined is not difficult to understand. Most people either reject it outright or accept it blindly, but let's take a closer look at how scientists arrived at this figure. To begin with, we now observe that the universe is expanding and cooling. Aside from forces like gravity that work to pull matter together, everything in the cosmos is moving away from everything else. This expansion is quantified by what we call the Hubble constant. The currently measured rate of expansion is such that for every million light-years of distance, space itself stretches by roughly 80,000 kilometers per hour. From the fact that the universe is expanding, we can draw an obvious conclusion. Matter is becoming more diffuse, and the distances between objects are growing. But there's also a less intuitive consequence. This expansion causes the wavelengths of light to stretch. This phenomenon is known as redshift. The extremely high-energy, high-frequency light waves emitted shortly after the Big Bang have had their wavelengths continually stretched as they traveled across the expanding cosmos. By the time they reach us, they have transformed into lower-energy microwaves. This is what we know as the cosmic microwave background B radiation, which we mentioned earlier. This is also why the James Webb Space Telescope is primarily an infrared telescope. The photons from galaxies billions of light-years away have been so dramatically redshifted by the universe's expansion that we now need infrared instruments to observe them. The higher a photon's energy, the shorter its wavelength, and the hotter it appears. Lower energy photons have longer wavelengths and appear colder. That's why we say the universe was once hot and dense, but has since become vast and cold. Estimating the age of the universe relies on a few key assumptions and several observational methods. First, based on cosmological principles, we assume that the universe is homogeneous and isotropic on large scales. That is, matter is roughly evenly distributed, and the laws of physics are the same everywhere. We also assume that the Big Bang was a global event, not a localized explosion. Under the framework of general relativity, these assumptions allow us to tightly connect the universe's age to its expansion history. Several approaches are used to measure that history. One is the standard candle method, which uses objects of known intrinsic brightness, such as type Ia supernovae, to estimate distances. By observing how bright they appear, we can calculate how far away they are, and therefore how long ago the light we see was emitted. Another method involves analyzing the cosmic microwave background radiation. By studying tiny temperature and density fluctuations in the CMB and linking them to the large-scale structures we observe today, like galaxy clusters, we can infer how the universe has expanded and evolved from its earliest moments. By combining these insights with the currently observed expansion rate, the Hubble constant, scientists can reconstruct the expansion history of the universe. They also take into account the estimated composition of the universe, about 68% dark energy, 27% dark matter, and just 5% ordinary matter. Using cosmological models based on general relativity and all the data described above, scientists can calculate the universe's age with remarkable precision. As for dark matter and dark energy, the truth is we still know very little about their true nature, but we can observe their effects. Dark energy is thought to be the mysterious force driving the accelerated expansion of the universe. Without it, the expansion should have slowed by now. Dark matter, meanwhile, reveals itself through its gravitational effects. Although we cannot see it directly, we can detect the gravitational pull it exerts, especially in galaxies and galaxy clusters, where the observed gravity far exceeds what visible matter can account for. Dark matter is considered essential for maintaining the integrity of galaxy clusters and the cosmic web-like structure of the universe. Scientists have even mapped out dark matter's distribution using gravitational lensing and simulations. Even though we don't yet know what it is, understanding its role is sufficient for estimating the universe's age. Knowing its function is enough. We don't need to know its essence. So, different lines of reasoning converge on a consistent estimate. We understand the current rate of cosmic expansion, the Hubble constant. We know how that expansion causes redshift. We have a model of the universe's composition: ordinary matter, and dark energy. We assume large-scale homogeneity and isotropy. We can observe the evolution of galaxies over time. We can analyze the fluctuations in the CMB, and by integrating all this information and applying the laws of physics in reverse, we can trace the universe's expansion all the way back to the moment of the Big Bang. In the early stages of cosmology, scientists employed three main observational approaches: measurements based on the Hubble constant, analyses of the cosmic microwave background, CMB, and studies of the evolution of large-scale structures. These methods, though focused on different aspects of the universe, have all yielded remarkably consistent estimates for the age of the universe, approximately 13.8 billion years, with a margin of error of just around 1%. So, do we truly have a definitive answer about the age of the universe? The most accurate statement would be, we have a very close approximation. As our observational technologies continue to improve, for example, with the upcoming Nancy Grace Roman Space Telescope and the already groundbreaking James Webb Space Telescope, new missions are specifically designed to peer deeper into the universe's distant past. If one day the estimated age of the universe is revised, it won't be surprising. On the contrary, it would be an exciting development. Honestly, although cosmological research has been underway for quite some time, we are still very much in the early stages of exploration. A few hundred years ago, who could have imagined that humanity would one day be able to estimate the age of the cosmos? Now we come to the third question. Why can a single element challenge the Big Bang model? How did it all begin? What did the early universe look like? Why did it even happen at all? Scientists, drawing from accumulated knowledge, developed a theoretical model known as the Big Bang model, an attempt to reconstruct the conditions of the universe's birth based largely on observational evidence, like elemental spectra. But anyone who has tried to complete a jigsaw puzzle knows the feeling. Sometimes you find a piece that just doesn't seem to fit anywhere. That sinking realization suggests that a mistake may have been made, though you can't immediately see where. In the case of the universe, that troublesome puzzle piece is lithium. So the core question arises: where did the universe's missing lithium go? Lithium is an alkali metal element with 3 protons, and it's one of the few elements that, according to Big Bang nucleosynthesis, BBN, should have formed in the first few minutes after the Big Bang. So how do we know there might be a problem with the model? According to the hot Big Bang model, the universe began from an incredibly hot and dense origin, expanding and cooling over time. Although it's difficult to describe the exact initial conditions, because physical laws break down at the very beginning, we do understand what happened shortly afterward. Between about 1 second and a few minutes after the Big Bang, as the temperature dropped to around 1 billion degrees, the strong nuclear force was able to bind protons and neutrons together. This led to the formation of large amounts of hydrogen, around 76% of the total mass, and helium, around 24%. The model also predicts that through much rarer nuclear reactions, trace amounts of lithium would be produced. Specifically, it forecasts that lithium should make up about 0.00007% of the early universe's mass. It is this precise prediction about lithium content that forms the heart of the lithium problem, because what we observe in reality doesn't match the model. This is the essence of the lithium mystery. Although the predictions of the Big Bang nucleosynthesis theory regarding hydrogen and helium align astonishingly well with observed abundances in stars and ancient galaxies alike, lithium presents a serious challenge. There are two major issues. First, the predicted amount of lithium-7, the most common isotope, is significantly higher than what we actually observe in the oldest stars, by about a factor of 3. In other words, these stars contain only 1/3 the lithium-7 the theory suggests they should. Second, the abundance of lithium-6, a far rarer isotope, appears to be anomalously high. Theoretically, lithium-6 should make up only about 2 in every 100,000 lithium atoms. Yet observations suggest it's up to 1,000 times more abundant than that theoretical prediction. These two major discrepancies, the shortage of lithium-7 and the surplus of lithium-6, together form what is known as the lithium problem, a persistent puzzle for cosmologists. What does the lithium problem mean for the Big Bang model? Does it mean the entire theory must be discarded? Not necessarily. When faced with a contradiction between theory and observation, there are typically two possible explanations. Either the theory is flawed, or the observations are incorrect. As for the theory, it is extremely difficult to completely dismiss the Big Bang model, given how successful it has been in explaining the observed abundances of hydrogen and helium, as well as the CMB. But the model is not perfect. For example, our understanding of the universe's earliest moments is still evolving. Even Stephen Hawking's views on the nature of the beginning changed over time. Perhaps future versions of the model will incorporate new physics or deeper insights into the early universe that allow us to resolve the lithium discrepancies without abandoning the model's core framework. On the observational side, measuring such minute amounts of lithium from the early universe is extraordinarily challenging. Most of the current data comes from analyzing the spectra of ancient stars. But stellar interiors can destroy lithium-7 or create lithium-6, meaning the surface abundances we observe may not reflect the universe's original composition. So it's also possible that systematic errors or observational limitations are responsible for the discrepancies. In the future, with more precise measurements, we may finally be able to reconcile the data with the theory. Until then, the lithium puzzle remains an open and fascinating frontier in cosmology. In short, the lithium problem either points to the need for revisions or additions to the Big Bang model, or it reflects the current limitations of our observational tools. Ultimately, any theory about the origin of the universe cannot be considered complete until all of its predictions are consistent with all available observational data. Whether it's the discrepancy in lithium abundance or other puzzling cosmic phenomena, every number must have a reasonable explanation. When it comes to the origins of the universe, there is still so much for us to learn. And yet, with nothing but telescopes and human intelligence, we've managed to deduce events that took place billions of years ago, even before matter itself had fully formed. That, in itself, is astonishing. The grand tapestry depicting how everything began is still waiting to be completed. Regardless of how the universe came into existence, it rests upon an underlying order, an order that allows us to uncover its principles, explore its mysteries, and reconstruct the evolution of its various parts. This brings us to the fourth question: what lies beyond the observable universe? In ancient times, people would sit around flickering campfires, pondering what unknown things might be lurking in the darkness. In that sense, our situation hasn't changed much. Today, our campfire burns brighter and spreads wider. Our vision has extended across the globe, and with the help of space telescopes like the James Webb, we've even stretched our reach to the farthest edge of the observable universe. Yet beyond that edge, darkness still descends, leaving a vast void for our imagination to fill. The boundary of the observable universe forms an insurmountable barrier. This is a region of space receding from us so rapidly, faster than the speed of light due to the expansion of space itself, that nothing, not even light, can ever cross that line to reach us. As a result, anything beyond that boundary is causally disconnected from us. Unlike the darkness our ancestors once feared, this modern edge of darkness may well be destined to remain a mystery forever. We cannot go there. It cannot come to us. At least, that's what we used to believe. But in 2008, a study analyzing the movement of hundreds of galaxy clusters found something startling. These clusters seemed to be drifting collectively toward a specific direction, toward the very edge of the observable universe. What was more puzzling was that the speed of this drift exceeded what existing scientific theories could explain. It was as though something beyond the edge of our visible universe was pulling on them, or had pulled on them in the past. This force seemed to stretch across billions of light years, hinting at the existence of a massive hidden structure lurking in the final darkness beyond. This mysterious large-scale motion of galaxy clusters has been given a name: dark flow. But what do we really know about it? What might be causing it? And what could it mean for our understanding of cosmology? Now we arrive at the fifth question. Is dark flow real, and what does it mean for our picture of the universe? Dark flow is a deeply controversial topic, so let's start with what we know for sure. In 2001, NASA launched the Wilkinson Microwave Anisotropy Probe, WMAP. Its mission was to map the cosmic microwave background, CMB, with unprecedented precision, the faint afterglow of the Big Bang still radiating across the entire universe. The goal was to help us better understand the fundamental properties of the cosmos. That map, completed in 2010, had a profound impact on cosmology. It helped scientists answer critical questions such as how flat the universe is, and what proportions of the universe are made up of ordinary matter, and dark energy. Alexander Kashlinsky led a research team at NASA's Goddard Space Flight Center. His team sought to compare the CMB map with known data on the movements of galaxy clusters to see if any patterns could be found. It was an immensely challenging task. To do this, they used a subtle phenomenon called the kinematic Sunyaev-Zeldovich (KSZ) effect. This effect is extremely faint. Simply put, the principle is this: when photons from the CMB pass through a galaxy cluster filled with high-energy electrons, they gain a tiny amount of energy through a process called inverse Compton scattering. Whether it's because the galaxy cluster is hot, transferring heat to the CMB photons, or because the cluster is moving quickly, transferring kinetic energy, the result is a slight increase or decrease in the energy of the CMB radiation as it passes through. The direction and magnitude of this energy shift depends on the motion of the cluster. By analyzing this change, researchers can infer both the presence of the cluster and its velocity relative to the CMB. The challenge lies in the fact that the signal is vanishingly small. It takes a statistical analysis of a vast number of galaxy clusters to detect it meaningfully. That's why the researchers needed a CMB map with extremely fine resolution. Only then could they cross-reference it with known cluster data to look for the possible imprint of this mysterious large-scale flow. Using the known positions of around 1,000 galaxy clusters, researchers conducted a comparative analysis to detect any large-scale patterns of movement. To their surprise, they discovered a distinct trend: a massive collective flow of galaxy clusters relative to the cosmic microwave background (CMB) frame. This movement spans at least 2.5 billion light-years of space around us, with clusters drifting together at speeds of 600 to 1,000 kilometers per second, heading toward the constellations Centaurus and Vela. The mystery lies in the fact that in that direction of the observable universe, no known structures, such as superclusters, are large enough to exert the gravitational force needed to explain this immense drift. This implies that there must be one or more enormous gravitational sources pulling on these galaxy clusters, and those sources lie beyond our line of sight, outside the observable universe, perhaps even further beyond. It's a highly controversial idea. But first, is it even possible for something beyond the observable universe to influence us gravitationally? You might instinctively say no. As explained earlier, once a region of space recedes from us faster than the speed of light due to cosmic expansion, it becomes causally disconnected, meaning no interaction is possible, not even via gravity, since gravity also propagates at the speed of light. However, there's a loophole. What if such influence occurred during a particular phase in the early universe, specifically before the period known as cosmic inflation? For those unfamiliar, cosmic inflation refers to a theory developed in the 1970s to address a long-standing mystery. Why does the universe appear so flat? And why are temperature and matter distributed so uniformly, even across regions that should have never been in contact? Physicist Alan Guth proposed that if, shortly after the Big Bang, the entire universe had once been tightly connected and in thermal equilibrium, like a perfectly mixed solution of dye and water, then underwent a period of extremely rapid exponential expansion, it would explain the observed uniformity. This period of expansion, called inflation, may have occurred between 10 minutes and 10 seconds after the Big Bang. Though incredibly brief, it could have caused the universe to expand by at least 10 square seats times, like a single bacterium suddenly growing to the size of the Milky Way in a fraction of a second. The beauty of adding inflation to the Big Bang model is that it explains why distant parts of the universe which appear disconnected today could have once interacted and achieved uniformity. So how does this connect to dark flow? The key lies in the idea that dark flow could be a relic of pre-inflationary conditions. Imagine that before inflation, the far regions of the universe were not perfectly uniform. Suppose that, just outside the region destined to become our observable universe, there was a zone of particularly high density. That high-density region would have exerted a strong gravitational pull on nearby matter, perhaps even tugging on the matter that now forms our local clusters. Then came inflation. The violent expansion flung that dense region far beyond our cosmic horizon, beyond what we can now observe. Although we are no longer directly influenced by its gravity, the matter it once pulled, including what became today's galaxy clusters, retains its momentum in accordance with Newton's first law. They continue drifting in the same direction long after the original source disappeared from our view. This, theorists argue, is what we may be observing today as dark flow. Still, the theory is controversial for two main reasons. First, it challenges the cosmological principle, which assumes the universe is homogeneous and isotropic on large scales. That is, matter is evenly distributed and the universe looks the same in every direction, with no preferred location. This principle underpins modern cosmology. The existence of dark flow implies that beyond our observable universe lies an unusually massive concentration of matter, disrupting that uniformity. In essence, the universe might not be as even as we believe. It could be far more chaotic once we cross the boundary of what we can see. This raises unsettling questions. What if we are merely cosmological lucky ones, residing in an unusually flat, balanced region of space? What would that mean for our theories of cosmic formation, and even for inflation itself? If inflation was proposed to explain uniformity, what does it mean if the larger universe is not actually uniform? Second, the observational evidence for dark flow is itself hotly debated. Kashlinski's team at NASA remains convinced they have detected it. However, the European Space Agency's Planck satellite team, using more advanced and higher resolution instruments than WMAP, re-examined the CMB and compared it to similar galaxy cluster data. After analyzing about 1,000 clusters, they reported no statistical evidence supporting the existence of dark flow. Kashlinski and his team, however, reanalyzed the same Planck data and claimed they still saw signs of the flow. As of now, the scientific community remains divided. Kashlinski's group has even announced plans to conduct deeper analyses combining Planck and MAP data to seek more definitive proof. But the results of that work have yet to be released. Until more reliable evidence emerges, the cautious approach is to assume that dark flow may not exist, or at least treat it with skepticism. In other words, we currently lean toward the belief that there isn't a cosmic monster lurking just beyond the edge of visible space, dragging thousands of galaxies toward it billions of years ago. And yet, like all things unknown, it stirs the imagination. Science does not care for what is more convenient or more compatible with our existing frameworks. Truth is truth, whether it is simple or complex. Maybe one day, in some way, we'll discover the final answer to what lies beyond the observable universe, and whether dark flow truly exists. But even then, We may simply find ourselves pushing the boundary of darkness further out, only to encounter a new cosmic horizon, and once again be drawn into reflection and discovery. The road to knowledge is endless. Humanity's hunger for truth and discovery will never fade.